In current electricity, now we study Faraday's laws. Self-inductance. To study self-inductance, let us take a coil of wire wound in the form of a spiral. A magnetic field will be created inside the spiral coil, and along the axis of this coil, if a current flow is established in the coil. Due to the current flow, a magnetic field is created along the axis of this coil. The magnetic field comes out of the coil if the current flow is in the anti-clockwise direction. The magnetic field goes into the coil if the current flow is in the clockwise direction. The direction of this magnetic field depends on the direction of current flow. Now, we can consider the coils to be situated in a magnetic field. The coils can be considered as though they are situated in a magnetic field. In fact, it is the magnetic field created by the current in the coil. So, the coils are situated in the magnetic field created by the current flowing in them. So, a flux is linked with the coil. The surface of these coils will be perpendicular to the magnetic field. Hence, the angle theta will be 0. The angle theta, that is the angle between the magnetic field direction and the area vector direction, is 0. So, maximum flux is linked with the coil. The flux linked with the coil is constant as long as the current flow in the coil is constant. As long as the magnitude of current is constant, the flux linked with the coil is constant. But the flux changes as the current changes, as the current flow changes. That is, either the current is increasing or decreasing, the flux linked with the coil changes. So the varying current produces varying magnetic field, and the varying magnetic field, it varies the flux created, the flux linked with the coil. This varying flux, it creates an EMF called induced EMF. So an induced EMF will be created whenever the flux linked with the coil changes. That is, whenever there is change in current in the coil. So, moreover, the flux linked with the coil will be proportional to the current. The flux linked with the coil will be proportional to the current. If phi represents the flux linked with the coil and I is the current flowing through this coil, then phi will be proportional to I. This proportionality is replaced with a constant called L, called as self-inductance. So phi is equal to Li, where L is self-inductance. Its value depends on the geometry of this coil. Now let us derive a relation for the self-inductance L. We have the relation phi is equal to Li, where phi represents the flux. The flux is given by BA. The flux linked with each coil is given by BA, where A represents the area of each coil. We know that the area of each coil is pi r square. The magnetic field induction inside this coil is given by B is equal to mu naught Ni by 2R. Mu naught Ni by 2R, where N is the number of turns per unit length, I is the current flowing in the coil, and R is the radius of the coil. So using these two relations, we can determine the flux linked with each turn of the coil. The flux linked with each turn, phi is equal to mu naught Ni into pi r square by 2R. Mu naught Ni into pi r square by 2R. So the total flux linked with the entire coil is given by mu naught Ni pi r square by 2R into capital N, where capital N represents the total number of turns of the coil. So mu naught Ni pi r square by 2R into capital N gives the total flux. So this, comparing this equation with phi I, phi is equal to Li, phi is equal to Li, we get the value of L as mu naught Nn pi r by 2. Mu naught Nn pi r by 2. So this is the relation for the self-inductance L of the coil. Before we define self-inductance, let us take the relation that is used for determining the induced EMF in the coil. the EMF will be induced whenever the current is varying. So the induced EMF E is given by minus d phi by dt. We know that the relation for induced EMF is minus d phi by dt. Taking phi as Li, we will get this relation as minus d by dt of Li. Therefore, E is equal to minus L di by dt. Minus L di by dt. This is the relation that can be used for determining the induced EMF in the coil. Now, let us pass on to define the self-inductance. For defining self-inductance, we can take the two relations. One is phi is equal to Li. The other one is E is equal to minus L di by dt. From the relation phi is equal to Li, if I is equal to 1 ampere, then phi is equal to L. So we can define self-inductance as the flux linked with the coil when unit current is flowing through the coil. This is one way of defining the self-inductance. Self-inductance is measured in henries. Now another way of defining self-inductance is from the relation E is equal to minus L di by dt. In this relation, if di by dt is equal to 1, then E is equal to L. So we define self-inductance as the quantity which is numerically equal to the induced EMF in the coil if the rate of change of current is 1 ampere per second. When the current is varying at the rate of 1 ampere per second, then the induced EMF in the coil, it will be numerically equal to the self-inductance. Like this, we define the self-inductance. Mutual inductance. To study mutual inductance, let us consider two coils. One is P, the other one is S. P represents primary coil, S represents secondary coil. These two coils are placed close to one another. A battery is connected to the primary coil through a tap key, and a galvanometer is connected to the secondary coil. Now observe the deflections in the galvanometer by closing and opening the battery key in the primary coil. When you press the tap key, you notice deflection. When you release the tap key, you notice deflection in the galvanometer. But there will be no deflection of the galvanometer when the key is kept closed. That means whenever the current in the primary coil is constant, there is no current in the galvanometer. But the current is shown by the galvanometer whenever the circuit is open or circuit is closed. That is whenever there is change in current. The current in the galvanometer is due to the induced EMF. I will explain how the EMF will be induced. So the current is created due to the induced EMF. Induced EMF is produced due to the change in flux. So a flux is linked with the secondary coil, and that flux is changing. Due to that change in flux, current is created in the secondary coil. Now let us consider only the flux created in the second coil, the flux linked with the second coil. If phi is the flux linked with the secondary coil and I is the current in the primary coil, remember that current is flowing in P, whereas flux is linked with S. So whenever current is flowing in P, a flux is linked with S. If that flux is phi and the current in the primary is I, then the flux linked with the coil S is phi is proportional to I. Phi is proportional to I, and this proportionality is replaced with a constant M. So phi is equal to Mi, where I is called mutual inductance of the two coils. Mutual inductance of the two coils. The value of this mutual inductance depends on the number of turns in the coils, the distance between the coils, the geometrical shape of the coils, the material of the core, and the angle between the axes of the coils. Mutual inductance will be maximum when the angle between the axes of the coils is 0. Now let us imagine the rectangular bar represents a soft iron core. The lines, dotted lines, represents the magnetic field, and over that Suppose two layers of wires are wound. The first layer, let us call this as primary coil, and another layer of wire is wound. Let us call the second as the secondary layer. The first layer, let us call it as primary coil, and the second layer of wire is as secondary coil. Let us connect battery to the first layer and galvanometer to the second layer. Now, whenever current is passed through the primary coil by closing the battery, a magnetic field is created. That magnetic field is represented by the dotted lines. Now, the secondary coil can be considered as though it is situated in the magnetic field created by the first coil. So, a flux is linked with the secondary coil because it is situated in a magnetic field. So, a flux is linked with the secondary coil. That flux is represented by phi. So, phi is equal to Mi. We have derived this relation. The flux is proportional to the current and flux is equal to phi is equal to Mi. Using this relation, we can define mutual inductance, coefficient of mutual inductance. When I is equal to 1 ampere, then phi is equal to M. So we can define M, the coefficient of mutual inductance, as the quantity which is numerically equal to the magnetic flux linked with the secondary coil when 1 ampere of current is flowing through the primary coil. Like this we can define mutual inductance. We can also define mutual inductance in another way by deriving a relation for the EMF, induced EMF. We know that the relation for induced EMF E is equal to minus d phi by dt. Minus d phi by dt. Now, using the value of phi is equal to Mi, we will get E is equal to minus d by dt of Mi. That is equal to minus mdi by dt. Let us use this relation for defining mutual inductance. We can define this by taking the following mathematical observation. If di by dt is equal to 1 ampere per second, then E is equal to M numerically. So we can define mutual inductance as, if the variation of current in one coil is 1 ampere per second, then the value of induced EMF will be equal to the mutual inductance. Like this we can define mutual inductance, coefficient of mutual inductance. The coefficient of mutual inductance is also measured in Henrys. The value of M will be 1 whenever, due to the flow of 1 ampere of current in the primary coil, if the flux produced is 1 Weber in the secondary coil, then the value of mutual inductance will be unity 1. Transformer works on the principle of mutual inductance. In a mutual inductance, we notice two turns, primary turns and secondary turns. Here P indicates primary turns and the number of turns in the primary is indicated by NP. S indicates secondary turns and NS represents the number of turns in the secondary. These windings are done on laminations, rectangular metallic frames, sheets, specially designed sheets. On these laminations, the windings will be done. Generally, an EMF will be applied across the primary. P indicates the primary. Across this primary, an alternating EMF will be applied. On the secondary, an induced EMF will be appearing. An induced EMF will be produced across the secondary. There are two types of transformers, step-down transformer and step-up transformer. In step-down transformer, the input voltage will be more and the output voltage will be less. The voltage across secondary will be less. This will be obtained if we consider the number of turns in the primary is greater than the number of turns in the secondary. If we devise such that the number of turns in the primary is more than the number of turns in the secondary, then it works as a step-down transformer. In step-down transformer, the input voltage is more and the output voltage is less. if the number of turns in the secondary is more than the number of turns in the primary, if NP is less than NS, then it works as a step-up transformer. That means the input voltage will be less. For a less voltage, the output voltage will be more. To increase the voltage, we use step-up transformer. To decrease the voltage, we use step-down transformer. Transformer works only on AC but not on DC. We have to remember that the transformer works only on AC but not on DC. Now I shall explain the principle involved in the working of a transformer and then derive a relation for the ratio of the EMFs. Whenever we apply an AC to the primary, that is an alternating current, an alternating magnetic field is produced. Due to this magnetic field, a flux will be linked with the coils. This flux passes through, that is the magnetic field, passes through the core between the two coils. If the core is a closed one, then there will be no loss of flux. So the leakage of flux will be eliminated if the core is a closed one. So we use rectangular strips so that they form closed loops. That is how we eliminate the loss of flux. Due to the alternating current, an alternating flux will be created. A changing flux will be created. So both the coils will be associated with changing flux. We know that whenever a coil of wire is placed in a changing magnetic field, the flux linked with the coil changes. Whenever there is change in flux, then an EMF will be induced. So in both the coils, EMF will be induced. If N1 is the number of turns of the primary coil, then the induced EMF in the primary coil is given by minus N1 d phi by dt, where d phi by dt is rate of change of flux. Similarly, the EMF induced in the secondary coil due to the same flux is ES is equal to minus N2 d phi by dt. So d phi by dt is the rate of change of flux with the secondary coil, and N2 is the number of turns of the secondary coil. Like this, we can calculate the EMF, induced EMF in the primary as well as in the secondary. So the ratio of the turns N1 by N2 can be obtained like this: ES by EP, induced EMF in the secondary by induced EMF in the primary. The ratio of the induced EMFs is equal to N2 by N1. The ratio N2 by N1 is called the transformer ratio. So the transformer ratio decides the ratio of the induced EMFs. Efficiency of a transformer. Efficiency of a transformer. Before we study the efficiency, define the efficiency, first let us study the powers. If IP is the current in the primary, then the input power is EP/IP. We have seen the induced EMF as EP. So if IP is the current, then EP/IP is the input power. Similarly, if IS is the current in the secondary, then the output power is ES/IS. ES is induced EMF in the secondary, IS is the current in the secondary, then ES/IS will be the power in the secondary. Here the EMFs and currents are all taken as RMS values because we are using AC currents and AC EMFs, so we consider them as RMS values. If there is no loss of power, then EP/IP will be equal to ES/IS. If there is no loss of power, then EP/IP is equal to ES/IS. The efficiency of a transformer is defined as the ratio of output power by input power. The ratio of output power to input power is defined as efficiency. Mathematically, it is given by eta is equal to P output by P input. P output divided by P input. So P output is the power, that is across the secondary. P input is the input power. Generally, we express this efficiency in percentages. So percentage efficiency is given by output power by input power into 100. Like this, we define efficiency. For an ideal transformer, the efficiency is 100. So if EPIP is equal to ESIS, then that is an ideal transformer. In ideal transformer, the efficiency is 100%. But due to loss of energy, the efficiency will be generally less than 100. It will be between 90 and 99%. Summary of this class. The flux linked with a coil due to the current flow in it is directly proportional to the current flow. If phi is the flux and I is the current, phi is equal to Li, where L is known as the coefficient of self-inductance. The rate of change of flux is proportional to the induced EMF. So E is equal to minus L di by dt. Minus sign comes due to Lenz's law. The flux linked with one coil is directly proportional to the current in another coil when they are placed side by side. The rate of change of flux linked with one coil is directly proportional to the EMF produced in the second coil. So E is equal to minus M di by dt. Transformer is based on mutual inductance. Its efficiency is defined by output power by input power into 100. So this is the essence of this class.